I'm debating making that the second class I do next year. So, physics and something. I don't know the other one. Discrete math is one.
What are you teaching right now?
Huh?
Teaching geometry and calculus.
Right now I'm doing calculus and geometry.
Next year, won't they need you to do geometry?
I'm not doing geometry again. I'm done. So physics and something, God decide what. Anyways, let's get started with today's material. Section 5.3. This section is all about definite integrals. And I told you that if I could get you to read just one section in the remainder of the book, it would be this one. Right? Do you remember that?
I remember.
Drilled that into your brain. You went home, you read it that night. So you're already familiar with all this, but let's just touch on it just to make sure, right? Let's remind ourselves of what we're talking about. What are we talking about? What's the calculus idea we're interested in?
Find the area of a curve.
Integrals, right?
Yeah.
Integrals. And what was our big idea for an integral? So the intuition we were using is that an integral gives me the area under some curve. So I've got some curve here, f of x, it is whatever it is, I don't know. And we want to talk about its area, starting at some point A, and going forward to some point B. Right? And how did we calculate this area? We did some integrals by hand last week. What did we do?
Rectangles.
Rectangles. We broke it into, so first I partition up my x-axis here between A and B.
Yeah.
I create some partition. Remember that a partition P was just some set of points, x naught, x1, dot, 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 xn. And that's just partitioning up this interval where x naught is A and x1, and xn is B. And so here's x1, which is also the same thing as A. Here's x2, here's x3, x4, x5, x6, x7, dot, 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 dot. Here's xn, also B. So we partition it up, and that's going to be the basis of our rectangles, right? And then with those, we create these rectangles. Now, how high do we make our rectangles?
The value of
Let's write down here at the bottom just the sum of these rectangles as we're going to help us see. So we're summing these things up. We're going to do the sum from k equals 1 to n. We're going to make n of these things because we partition it into n pieces. Sorry, x naught is this one. And then x1, x2, x3, dot, 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 xn. So we divide it up into n pieces. With me so far? And we're going to add up all these areas. Length times width, over and over again. Or base times height, probably a better way to say it. So we got to get the height of one of these rectangles. How do I know how high to go?
F of x.
Well, I use the function f, but how high for this rectangle?
Whatever the point is.
Which point? Do I find the height at this point? Do I find the height at this point? Do I find the height at this point? At this point? Which point do I use?
Doesn't matter.
And it doesn't matter. So we say pick any point in your first interval, and we're going to call that point C sub 1. C sub 1 is a random point between x naught and x sub 1. That's what C sub 1 is. C sub 2 is some random point in your second interval. So over here, for our kth one, remember we're always thinking about some kth rectangle. The point that we pick in here is just C sub k. Sorry, that's a dead spot on the board. C sub k is some random point in the kth interval. So for this rectangle right here, its height is just f at C sub k, whatever that is, times, what was the notation we used for its width? You remember this notation? Delta x sub k. Delta x sub 1 is x1 minus x0. Delta x sub 2 is x2 minus x1. Dot, 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 delta x sub k is that point minus that point. What does that point minus that point give me? It gives me the distance between them. What's the distance between 3 and 5? It's 5 minus 3, or 2. What's the distance between that point and that point? Their difference, which is what the delta x notation symbolized. So this now is summing up that area with those rectangles. You with me? Now, how did we make it perfect? We take a limit as what?
As delta x equal to 0.
As the delta x goes to 0, kind of. It's not really a fixed number. this one is wider than that one. So these rectangles aren't necessarily all the same width.
As the partition goes to 0.
As not the partition goes to 0. I don't know what it means for a partition to go to 0. A partition is a collection of points. We keep adding more and more points to our partition, breaking the rectangles up more and more.
The distance of the point in the partition?
The distance between the points in the partition goes to 0. So we have this notation, the norm of the partition, or sometimes called the gap of the partition. What is a norm or the gap of the partition? It's the biggest distance between any 2 points.
Oh, yeah.
So this, in this picture, this would be the biggest base of our rectangle. So in this case, it probably refers to delta x sub 1, because that looks like it's the biggest base. You with me?
Yeah.
And so we want as that goes to 0. As long as the gap of our partition that we're using to get our base goes to 0, then this method in the limit works. Now let's read the definition that is in your textbook to make sure it makes perfect sense. So, let f of x be some function on the closed interval a to b, just like our picture so far. We call j is going to be what the calculation is here. So we're going to say the limit as our partition's norm goes to 0 of the sum from k equals 1 to n of f of c sub k times delta x sub k. We're going to call that whole thing j. It's going to be what the limit evaluates to. That's the j in this definition. So we call j the definite integral of f over ab. Notice that when I calculate the area, it spits out a number. So j is just a number. Okay. So j is the definite integral of f over ab, and the limit of the Riemann sums. What are the Riemann sums? They're those inner sums we were doing. The Riemann sums were one of our approximations. That was a Riemann sum. Right?
Yeah.
So that was, I don't know if I've used that name before or not, but that's just what a Riemann sum is. So it's the limit of the Riemann sums, that exact thing, provided that, what? For every epsilon, there exists a delta greater than 0, such that for any partition you choose on the interval, then, if the gap is less than delta, then the Riemann sum is less than epsilon away from j. If our partition gap is smaller than delta, then our Riemann sum's distance from j is less than epsilon. As our partition gap here gets closer and closer to 0, then our Riemann sum gets closer and closer to j. This is just like our definition of a limit.
Oh, yeah, gotcha.
Yeah, go back to our definition of a limit. Let me write it a little bit more dense notation. What do we mean by the limit as x approaches c of f of x? What was the definition of that?
For all
It meant for every epsilon,
there exists a delta.
there exists some delta such that if x is within delta of c, so the distance between x and c is less than delta, that implies that the distance between f of x, oh, yeah, and L, I forgot to say this equals L. So the limit as x approaches c of f of x equals L. What does it mean to say that limit equals L? It means that for every epsilon there exists a delta such that if x is within delta of c, f of x is within epsilon of L. So that's less than epsilon. Sorry, going off the screen a little. Right? You see how this is almost saying the exact same thing.
Yeah.
If the distance from P, or the distance of the gap, is less than 0, or is within delta of 0, that's what it means for this to be less than delta. It means it's within delta of 0.
Yeah.
So as this gets really, really small, or sorry, as this gets really, really small, this gets really, really small. We can always find the delta small enough. We can always partition it up small enough. You tell me, I want you to approximate the area within 0.0001% of the actual area. I can always find a small enough way to partition this up to get within that margin of error. That's one way you can think about it. Okay, so that was exactly our definition of a limit. Here's the way I'm going to write it out. What are we saying? We're saying that the definite integral from a to b of f of x with respect to x is equal to the limit, as our partition gap goes to 0, of the Riemann sum.
That's the loss of it.
It's the exact same thing. It's just this is using more dense notation. Because we already know what a limit is. Here's our definition of a limit.
Yeah.
Throw this into there. So we're replacing, this is a partition of c minus 0, or in other words, the partition less than delta. And this is our Riemann sum. This one's using an L rather than this one used a J. But it's just taking this and throwing it in that definition.
So why even bother doing that instead of just taking
Because the author wants to make good and sure that you didn't forget what a limit was. So he's respelling it out. Rather than just giving you this.
Is there not a universal?
This says the same thing as this.
That's it.
He's just afraid that you don't remember this.
Is there a universal definition of an integral?
That-
Of a definite integral, that's it. That is the definition of a definite integral.
So why does he gonna make it?
Oh, you're asking is there like a unified one?
Yeah,
They
isn't
make
outside
the
of this textbook?
they
It
make the
doesn't
same
calculate.
They say the same thing. He's just respelling out what a limit. He's just not using limit language.
Yeah. This is it.
Okay. Alright,
They say identical things. It's like saying, is there a universal way to write 6? Is it okay to write it this way?
Yeah.
yeah.
Sure. So you can write the exact same definition a few different ways, and it's still the exact same definition. So here's the definition. Here's the way I'm always going to write it. The author re-spelling it out for you in case you forget what it means to talk about the limit as something approaches 0, or the limit as x approaches c again. So that's why he's re-spelling it all out. Okay. Now notice that in our Riemann sums, we could use any partition we wanted as long as its gap went to 0. And furthermore, we could pick any point we wanted to get our height of a particular rectangle. In our concrete case, if we ever have to calculate one by hand, what we're going to do is we're going to evenly divide these things up, always and forever. That's much easier to work with.
Yeah.
And I'm going to just always pick the right-hand point to calculate the height of each rectangle. So it's a special case. It's going to be a special case of this sum.
Yeah.
Notice that this is telling us there's an infinite number of ways we can sum these things up. There isn't the right way. If we're going to actually perform a sum, we need to pick some way to add them up. And so this is the way that I am going to add them up. It's just a special case of this. So let's re-see where this formula comes from and make sure that makes sense. So this time, let's say that I partition this thing up, but I divide it up into m pieces. Don't let my picture lie to you. Let's say I divide it up into m pieces where they all have the exact same base. How big is the base of my cake rectangle?
It's as big as all the other ones.
Now let's write this out. We're looking for the sum from k equals 1 to n. I'm going to add up my k rectangles. Let's see, what's this total distance?
It's B minus A.
B minus A. You see that? So if I divide that up into n pieces, n equal size pieces, what's the base of this one?
It's B minus A over N.
It's just b minus a over n. And the base of this one?
It's
B minus a over n. So they all have bases. B minus a over n is the base of every single one of those rectangles.
That makes sense.
You with me?
Yes.
Now, if I'm going to use the right-hand point to calculate the height of my rectangles every single time, what is the right-hand point? So this point is A. What is this point right here?
A plus N.
Or plus B minus A over
A plus B minus A over n.
Right.
That point is A plus B minus A over n. A gets us from 0 to here, plus the base of the rectangle gets me to that point.
Yeah.
Oh yeah.
Okay, and what's that point?
You just throw a
N
K on
times
the
A plus B minus A over N.
You got
It's
K.
A plus 2 B minus A over n.
Which would be K.
And this one is A plus 3 B minus A over n.
So it's K.
3 bases. And in general, for our kth one, this one right here, its base is, or its right-hand point, let's point to the right-hand point, is a plus k times b minus a over n.
And that's what you.
And so now we can calculate our Riemann sum. Here is a particular Riemann sum. We can take the sum from k equals 1 to n of, we're going to use the right-hand point to get our height, so a plus k times b minus a over n, and then multiply by the base, b minus a over n. And that's the Riemann sum that we're going to use. And when we calculate our integral now, we're going to take the limit of this as n approaches infinity. As n approaches infinity, then our base over here is getting closer and closer to what? 0. And so it counts as a Riemann sum. So just remind us this was a plus k times b minus a.
Zero them out because the numbers can be so small.
Does it zero them out? We've calculated some of these limits by hand, and it did zero out.
I know, but
Because
it's so
n's
small.
ended up canceling out.
Right.
Okay.
Because notice, as n gets bigger and bigger, k also gets bigger and bigger. And so you've got a denominator getting bigger and bigger, and a numerator getting bigger and bigger. And they grow in such a way that it turns out they cancel out in the limit.
Why does k get bigger?
Because we're going to add up a k all the way to n.
Oh,
So we're going to plug in 1 for k, 2 for k, 3 for k, all the way up to plugging in infinity for k, if n's infinity. And so how exactly do those things cancel out? Sometimes you can't just squint at it and know. You have to take the time to do the math. Good so far? Okay. So that's what we'll be using. The definition, if I ever have to calculate one by hand, I will say that the integral from a to b of f of x with respect to x is equal to the limit as n approaches infinity of this thing. And that's just using the right-hand points. This is a special case of this. That make sense? Okay. Now, theorem 1, we're not going to prove this, we're just going to say it. If f has at most finitely many jump discontinuities on some closed interval ab, then f is integrable on ab. We're going to be very interested in when can we actually calculate an integral on these things? What functions can we actually calculate an integral of?
Why can't we do that for every function?
Good question. So first, let's understand what the theorem's saying, and then let's see why we can't do that for every function. So this function is saying that if I've got some function, and it goes along like this, on some interval a to b, then the theorem is saying that we can integrate it. We can find the area underneath the curve. And what would be the idea? Well, you can calculate the area of this portion, and then the area of this portion, and then the area of this portion, and add them all up. Make sense?
Yeah.
Okay. So now, what about, why can't we do it with every function? So we're going to look at this function now, f of x, and it's going to be f of x is equal to, we are going to have it spit out a 1, or, well, we'll say a 0. It's going to spit out a 0 when x is not a rational number, and we're going to spit out a 1 if x is a rational number. Remember what a rational number is?
Yeah.
So let's plot this really quick over here. Let's see what happens when we plug in. So here's 1, here's, and then here's whatever. I don't know. We'll just call that 2, 1, whatever. What do I get when I plug in a fourth to this function?
Yep.
Is the fourth rational or irrational?
Rational.
It's rational. So when I plug in a fourth over here, I get 1.
Is it-
What do I get when I plug in a half?
Same thing.
1. What do I get when I plug in 1?
1.
1. What do I get when I plug in 1.001? 1. When I plug in 1.002, 003, 004, da 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 da. And when I plug in any rational number, it gives me a 1. Right?
Yeah.
Now what happens when I plug in the square root of 2?
Yeah. 0.
I get 0.
Why?
Because the square root of 2 is not rational. It's irrational.
I know, but technically it adds up to any number, but I can't put that in
Is how you
My
find-
function is, I spit out 0 if you plug in irrational, and I spit out 1 if you plug in a rational. That's my function.
Okay.
Here's my function's definition.
The name is-
Square root of 2 is irrational, so it goes right there.
Okay.
Right?
Yeah.
And I could do square root of 2 divided by 1.1,
Yeah.
which is going to be slightly smaller than the square root of 2. That's also irrational. And divided by something a little bit bigger, and that's also irrational and irrational. And if I were to plot all the irrational numbers, there's an infinite number of them. So here's all my rationals, here's all my reals. Now this is a function. It passes the vertical line test.
Yeah.
If you draw a vertical line, it intersects one and only one point. If it intersects a point up here, it misses a point down here.
What the heck?
And if it intersects a point down here, it misses a point up here. Now I can't draw these things. This is an unplottable function. Why is it unplottable? Because I can't draw a point. Every time I draw a point, I draw it with some area. Points don't have areas. So if I try to plot these things, it's going to look like a solid line right here, and it's going to look like a solid line right here. Nothing I can do about it. If we plotted every single point, right?
Why can't we take the area of that?
So now, let's calculate the area of it. We're going to use upper sums and we're going to use lower sums. You with me?
Yeah.
Okay, so starting out by using upper sums. So that means partition this interval up however you want, I don't care. And now, we are going to use the highest point that the function reaches on that interval.
Oh.
So for this little interval, every little interval is going to contain for sure a rational number.
Yeah.
So the rectangles are all going to look like this. Boop, boop.
Oh, what?
Because I'm using
Yeah.
the highest point reached in that interval to get the rectangle's height.
Right.
And your interval can't be one number.
And let's pretend that we were doing this on the interval from 0 to 2. So then this Riemann sum gives me what area? 2. Right?
Seems fine.
And if I take smaller partitions, it's still going to do the same thing.
Is there a problem?
So when I take the limit of that Riemann sum using upper sums, then I'm going to get, it evaluates to 2. Now, let's instead this time do it again. And our Riemann sum, we're going to use the lowest point the function reaches to calculate the height. Now what does my rectangle look like? Well, here's the first one. Here's the second one. Here's the third one. Here's the fourth one. Because on every interval, it achieves, every interval will always contain an irrational number,
Right.
no matter how small you make the interval.
Right.
And so all those rectangles will have a height of 0. Now add up all those rectangles and what do I get? 0. And you might remember going all the way back, a limit only exists if it doesn't matter how you take the limit to get the number. So the point is this limit doesn't exist. If there's 2 different ways I can evaluate it, the limit doesn't exist. Every Riemann sum has to give you the same number to say that the function is integrable, to say that the limit exists. It has to give you the same number no matter how you make your rectangles. So when it is integrable, then we can choose to take our rectangles however we want. And we typically choose to do it this way. That's an arbitrary choice.
Gotcha.
Interesting.
So it sounds like most functions will be integrable.
I don't know what most means.
I mean, most of
The functions that we deal with in Sanity Land will be integrable. Most of the ones that you work with. But not every function is integrable.
Yeah, that seems like a very specific case.
Well, sure. Simple counterexample where you can't integrate any piece of that thing.
Yeah.
There's nothing you can do. Because there's just a bunch of points all over the place.
That's a very interesting function.
It is. It's a very strange function. Okay. So, we talked about that. We talked about why it's not integrable. One more thing I want to stress is, here I say the integral from a to b of f of x with respect to x. Here I say the integral from a to b of t with respect to t. The x and the t here are just dummy variables. It doesn't change anything. I can put any variable I want in there. It doesn't change anything. It's just a dummy variable. So don't fall in love with these x's in there. And we're going to use x's as standard notation. There's nothing special about it. It's just common notation. Okay, so properties that integrals are going to have. So let's look at some properties. So let's say that I know that the integral from a to b of f of x with respect to x is some number, we'll call it j. You with me? 10 or whatever it is. What then is the integral from b to a of f of x going to be? What happens if I take my integral the other way?
It has to be the
Same
same thing.
thing?
Yeah.
Yeah. Area would change.
What would happen if I swapped all my b's and my a's in this?
Oh, it'd be
Wait.
negative.
It turns negative. So if you swap the direction that you take your integral, it flips it negative.
Yeah.
Does it give you the same number?
Yeah, it's the same number. It just gives you the negative of that number. The only thing that would change here is that my base here would be swapped.
Yeah.
So swapping your a's and your b's, all it does is change the sign. And that's all it does. So the integral from b to a of f of x with respect to x is the same thing as the negative of the integral from a to b of f of x with respect to x. Or in this particular case, it would be negative j.
Yeah.
Okay.
Make sense? Okay, let's look at our next one. What is the integral from a to a with respect to x of f?
0.
This is asking what is the area under a single point?
It's gotta be 0.
I'm going to start at A and I'm going to go to A.
Yeah, it's
What's the
zero.
area under that point? 0. So the area under a point, that's 0. Now both of those are technically by definition, but just trying to give you intuition for it. Okay, next one. What is the integral of k times a function with respect to x? Well, it turns out we can pull that k out, and that's k times the integral from a to b of f of x with respect to x.
Sweet.
Or in other words, in this case, it would be k times j, if that integral evaluated to j. Now, how do I know I can do that? Remember, what is an integral?
So,
It is a limit of a sum, right?
yeah.
And I know that I can pull a constant out of a sum. We've been doing that a bunch.
Yeah.
So I can pull it out of a sum, and I can also pull it out of the limit. We already proved, going way back, that the limit of a constant times a function is the same thing as the constant times the limit of the function.
Right.
So you can pull k's out of sums, and you can pull them out of limits, so you can pull it out of the sum and the limit. That make sense?
Yeah.
All right, the next one. The integral from a to b of f of x plus or minus g of x. When you do the integral of the sum of two functions, that is the same thing as the sum of the integrals.
Makes sense.
Same thing with the difference. And it should make sense. We already proved, remember, it's just a limit of a sum. And last time we went over how a sigma of a sum is the same thing as the sum of the sigmas.
Yeah.
Same concept, and the sum of the limits, or the limit of a sum is the sum of the limits. So you're applying both those principles if we were to prove this out by hand. And that's all it's using. That make sense?
Yeah.
All right, finally, well, not finally, next one. The integral from a to b of f of x dx plus the integral from b to c of f of x with respect to x. What does that give me?
The integral of a to c.
The integral of a to c. Can everyone see that?
A to B, B to C.
So let's draw out some function here. Here's a, here's b, here's c. The integral from a to b gives me this area. The integral from b to c gives me this area. So the integral from a to b plus the integral from b to c just gives me
A to C.
the integral from a to c of f of x with respect to x. So that's a very useful one for changing our bounds on our integral. Okay, next one. If f is continuous on some closed interval ab, then there exists some little m, which is the minimum value of the function, and some big M, which is the max value of the function, such that little m times b minus a is less than or equal to the actual area is less than or equal to big M times b minus a. Let's draw out a picture for this, and I think it will make perfect sense.
Okay.
So we've got some curve here. There it is. We're going to take it on some closed interval, a to b. You with me? First off, the function achieves a minimum value right here, call it little m, and it achieves some max value right here, call it big M. You with me?
Yeah.
Now using little m, what is the area of this rectangle?
It's B minus A times M.
A or B minus
M times b minus a, right? The height times the width.
Yeah.
Oh, yeah.
And if we went all the way up instead to big M and created this rectangle, what does that equal to?
Big M times
Big M times b minus a. And then what is the actual area under the curve?
something in between.
That is the integral from a to b of f of x with respect to x. And notice that it's going to be less than or equal to that and less than or equal to that. It's going to be sandwiched between those two values. That's all that that's saying.
Yep.
With me?
Yeah.
And then the last one, pretty intuitive. If f of x is always greater than or equal to g of x on our interval, then the area under f of x is always going to be greater than or equal to the area under g of x on that interval. Good? All right, let's do some examples really quick using these properties. You're going to tell me what these are. So let's start right here. I am giving you right here that the integral from -1 to 1 of f of x is equal to 5. The integral from 1 to 4 of f of x is equal to -2. And the integral from -1 to 1 of h of x is equal to 7. That's given. All right, question. What is the integral from 4 to 1 of f of x?
2.
2. How is he getting that?
Rule 1.
Oh, it's what you sign.
We know the integral from 1 to 4 of f of x is equal to -2. So what is the integral from 4 to 1 of f of x equal to?
2.
Just 2. It's just the negative of whatever that was. When you swap the bounds, it just makes your integral negative. So we were just using this property right here. Property 1. You see it?
Yeah.
Let's try another one. What is the integral from -1 to 1 of f of x plus h of x with respect to x?
Oh.
Well,
I know that the integral from -1 to 1, remember the integral of a sum is the sum of the integrals.
Yeah.
So what's the integral from -1 to 1 of f of x?
That's 5.
5. Plus the integral of h of x, perfect. So you're seeing that is just 12.
Yeah.
All right, finally, what is the integral from -1 to 4 of f of x? Not from 1 to 4, from -1 to 4.
It is 3.
3.
Yeah.
How's he getting that?
because he's
-1 to 1.
joining them together.
1 to 4.
Yeah, the integral from -1 to 4 is the same thing as the integral from -1 to 1 plus the integral of 1 to 4. So the integral from -1 to 1 of f of x is 5 plus the integral from 1 to 4 of f of x is -2. And together that gives me 3.
Yeah.
Now how on earth does an integral ever come out negative?
It goes underneath that.
If it goes underneath the x-axis, then all your heights are negative, and so in the sum, the f right here is going to spell out a negative number.
Yeah, gotcha.
Okay. So now, we are going to take the time to actually prove just property 6 out of these.
Why?
To prove it.
Okay.
What good is coming here if I don't ever prove anything for you?
Well, I'm just wondering why 6 specifically.
We're going to use 6 specifically for our other theorems. Today we are proving what's called the fundamental theorem of calculus. That's what the next section is. 5.3 is definite integrals. 5.4 is the fundamental theorem of calculus. The most fundamental theorem in all of calculus is what we'll be proving today. And this will be something we need along the way. Second reason to prove it is to try and just get you comfortable with this sigma notation and not get lost in it. It's one that's pretty intuitive. We already have the picture right there. Now let's just spell out the proof and get you comfortable with the notation. Okay, so what are we going to prove? Going to prove if f is, I'll just do cont like that for continuous since we have to say it right a lot. If f is continuous on AB, comma, then there exists little m and big M such that little m times b minus a is less than or equal to our integral from a to b of f of x with respect to x is less than or equal to big M times b minus a. Right? So 1, let f be continuous on AB, comma, AB, comma, let little m equal the minimum value that f achieves on AB, comma, and let big M be the, what's big M? It's the max value that f achieves on AB, right? Sorry, that was quite perfect. Okay, so now what? So we're trying to prove this big inequality, so 2. Then, let's see, what is M times b minus a equal to? Notice that b minus a, what is that?
Distance.
It's this total distance, right?
Yeah.
And so that is the same thing as, see if you can follow this. This is the same thing as m times the sum from k equals 1 to n of all your delta x sub k's.
Okay.
For whatever your partition is that you use to create your Riemann sum, those are the bases of all your rectangles. If I add up all the n of the bases of my rectangles, what do I get? I get b minus a, the total distance.
Yeah.
So the total distance is just adding up all the bases of the rectangles. That's what that notation's saying. You with me? And then, if I have m times a sum, what can I do with that m?
You can bring it on the inside.
I can take it on the inside if I want. So I'm going to take it on the inside. I'm going to stop writing the sum from k equals 1 to n. I'm just going to say the sum and expect you to know that it's from k equals 1 to n. So times the sum of m times delta x sub k. You with me?
Yep.
Now what is little m? It is the smallest value that our function takes on the closed interval a to b.
Yep.
So for sure, little m is less than or equal to the height of our function at any point. So if I replace m with the height of the function at some point c sub k, I could have only made my sum bigger.
Yeah.
And this is times delta x sub k, right?
Yep.
So replacing little m with the height of the function at each of the rectangles could have only made my total sum bigger. Because this is the smallest value the function takes, these are just a bunch of values that the function takes.
Oh, I see your connection.
Okay, and now this is going to be less than or equal to the sum of big M times delta x sub k. If I replace the heights of all my rectangles with just the highest point the function achieves, I could have only made my sum bigger. With me?
Yeah.
And now, what's that equal to? I'm going to pull my m out. So that is equal to m times the sum of all those delta x's.
Oh, you're good. And then you can just substitute it back.
And now, what is the sum of all the bases of my rectangles equal to?
It'd be minus
b minus a. So that's equal to big M times b minus a. So little m times b minus a is less than or equal to our Riemann sum, is less than or equal to big M times b minus a. With me so far? Now, we just take the limit. So 3. Then, the limit, as our gap goes to 0, of little m times b minus a, then has to be less than or equal to our limit, as our gap goes to 0,
Big M times
of our Riemann sums, which then has to be less than or equal to
big M.
the limit as our gap goes to 0 of big M times b minus a. Now you might remember that one we proved forever ago, that if a function is always greater than or equal to another function, then its limit is always greater than or equal to the limit of the other function. That's what we're doing here. I know that this is always less than or equal to this, therefore the limit of this is always less than or equal to the limit of this. Similarly, the limit of this is less than or equal to this, therefore the limit of this is less than or equal to this.
Yeah.
Okay? And so then, what do we get? What is the limit of this as our gap goes to 0?
It's the integral of that.
0.
What is the limit? Look, b constant, a constant, b minus a constant, m times b minus a constant. The whole thing's just a constant.
Oh, so 0.
What's the limit of a constant?
0.
Oh, so it's 0.
What is the limit of 2 as x approaches infinity?
Oh, it's 2.
It's 2. A constant's a constant.
Yeah.
But isn't M approaching 0 because it's the biggest point?
Little m is just the highest point in that interval. It doesn't matter how you break this up. The highest point is still the highest point in the entire interval.
Yeah.
Okay.
Little m is the highest point the function takes in the entire interval a to b.
And that doesn't.
Our limit is as we break this up into more and more rectangles.
The base. Okay.
Right. What is the lowest point this function achieves? You say, it's right here, it's little m. I say, aha, but what if I break my rectangles up like this? Now what's the lowest point the function achieves? It's the same, it couldn't care less how you break it up. Okay, that's what we mean. So, now, what is the limit, as our partition goes to 0, of m times b minus a?
M times B.
M times b minus a. The limit of a constant?
It's
A constant. So then we get m times b minus a is less than or equal to, what is the limit of our Riemann sums as our gap goes to 0?
The integral of that.
That's the integral. That's the definition of an integral. That is the definite integral from a to b of f of x with respect to x. That's its exact definition. That's what an integral is. It's the sum of all those rectangles as our gap goes to 0. Right? And that has to be less than or equal to, what is the limit now of m times b minus a?
M times B.
No, this one's not a constant.
Yeah,
Yeah, it is.
Yeah, it is. Good answer. M times b minus a. Alright. And that's why we take the time to prove stuff like that. Even though it's intuitive to you, it's very easy to confuse yourself as you start looking at all this notation. I want you comfortable with the notation. Good? Okay. So now, let's use that. Let me move my camera here so I don't have to remember to do it later. You can ignore the stuff on the far right, that's just my own scratch notes. Let me see how far this
That's not
goes.
examples.
Get the whole thing in case I never reference it. Okay. So now, now we're going to do an example. And we need to prove that the integral from 0 to 1 of the square root of the cosine of x plus 1 with respect to x, we want to prove that this is less than or equal to the square root of 2.
Okay.
Let's just briefly scratch this out. So, whatever this function's doing, here we'll say is the square root of 2. Here's 1. When is cosine at its biggest value? When is your x-coordinate at its biggest point? Zero. When the x is 0.
Right.
And then it only gets smaller from there. Right?
Okay.
So the biggest cosine of x, what's the biggest value cosine of x can spit out?
1.
1. That's the biggest value it can possibly spit out.
Yeah.
And so 1 plus 1 is
2.
2. The square root of 2 is the square root of 2. So this function, whatever it looks like, at 0 it starts out in the square root of 2, and then it must be getting smaller. Right?
Yeah.
And so the highest value that this function takes, the max value, the max f on our interval is equal to the square root of 2. Right? And using what we just barely proved, we know that the integral of this thing is less than or equal to its max value times the base. What's our base here? 1. So in other words, this rectangle has an area of square root of 2. And so the colored in area must be less than or equal to the square root of 2. Right?
Yeah.
So our big M here is the square root of 2. So just using this, we know that the integral from 0 to 1 of our function, cosine of x plus 1, with respect to x, we know that that is less than or equal to our highest point our function achieves, big M, times our end point minus our start point. There's writing it out completely explicitly. This is less than or equal to m times b minus a. M times b minus a is the area of this rectangle, and our actual area, the colored in part, has to be less than or equal to that, using exactly what we just proved here. That make sense?
Yeah.
Okay. Now, the author wanted to calculate some integrals by hand. So, next one he wants to do, our example, is we're going to calculate by hand the integral from 0 to b of just x with respect to x.
On the other question, we didn't even do anything. We just rewrote what it said.
Basically. Right? Yeah, it was almost a nothing. Okay. So, now we're going to calculate this integral by hand. You with me? How do we calculate that integral by hand?
A lot of sums.
If you can't remember how to do it, there's just that formula over there, but if it's throwing you off, let's just re-scribble it out. So our function is just a line, it's just x, so that's just a 45-degree line. You with me?
Yep.
There it is. And we're going from 0 to b. Here's b. Question, if we go over b, how high up did we go?
B.
B, because it's a 45-degree line. It goes,
Go over B, we went B.
if we go over b, we go up b. If that is a perfect 45-degree line, and it goes, if you are holding up a ramp at 45 degrees,
Yeah.
and you are 5 feet away from the base of the ramp, then you're holding the ramp 5 feet in the air. If this line goes over b, then it must have gone up b.
Yeah.
So the coordinates of this point right here are bb.
Okay.
Good? Okay. We are going to break this up now into our rectangles. I'm going to personally use the right-hand point. Nothing special about it, it's just what I'm going to use. You with me?
Yeah, okay.
So let's write out our sum here. What is the sum we're looking for? So we're looking for the sum from k equals 1 to n. I need to come up with my Riemann sum. So I'm going to divide this up into n even pieces. And I'm going to use the right-hand point to get my rectangle. And I'm going to take the limit as n approaches infinity. That will give me my integral. Good so far? Okay. So, let's see. What is the base of one of my rectangles?
It's K, B
The
minus...
width of the base. Just the width of the base.
Isn't it K, B minus A over...
Stop looking at the formula. It's confusing you. And just look at this. What's this total distance?
It's B.
B. So what is the base of one of those rectangles?
B over N.
Just B over N. So the base is B over N. And now, what is the right-hand coordinate? What are the coordinates of that point?
That's one. Just B over N.
That one's just B over N.
Right.
We just went that distance over.
That's K times B over N.
What's this one?
2.
2B over N. And by the time we get to our kth one,
That's K times B over N.
then this right-hand point is K times B over N. Okay, so I think you got it. So now this is going to be F of our right-hand point, which is K times B over N, times B over N. Now notice, that is identical to this formula, just where A is 0.
Oh, right.
It wouldn't be 0 if you had distance up.
Right, in this particular case, we're starting at 0. We're in a concrete case where we're starting at 0.
Yeah.
Okay. So what does this sum equal? This is equal to the sum from K equals 1 to N of, we got to plug this into our function. What is F of K times B over N?
That's K times B over N.
It's K times B over N. What's our function? It's a function that spits out what you input.
Yeah.
What's F of 6?
6.
6. What's F of B? B.
Oh.
What's F of 19? 19. What's F of K times B over N? K times B over N. So this is now K times B over N. And then we're multiplying that by B over N. With me? Okay, so now let's see what that equals. I'm going to pull both the B over N's out, because these are constants. So that's going to be B squared over N squared. Pulling them both out, multiplying them together.
Yeah.
Times the sum from K equals 1 to N of K. Now what is the sum from K equals 1 to N of K equal to? What's 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to N? What is it?
It's its own
It's N times it's N.
It's not N. 1 plus 2 plus 3 is not 3.
Oh, it's N times K. We have
1 plus 2 plus 3 plus 4 is 10.
It's N plus times N plus 1, isn't it?
So close.
We did this.
Yes, we did this last week. And you guys did your homework, so you had to use this a lot, and so you got it memorized. That's why you're all screaming at the same time. N times N plus 1 over 2. You're so sick of using the formula.
Oh, yeah.
Oh, yeah.
Oh, yeah, it's all coming back to me. All right, let's cancel out an N top and bottom. So we'll cancel that out with one of those. And then we'll distribute the B squared to each of those. So this is going to be equal to B squared times N plus B squared all over, well, I'll do it all together in one go, keep it together for a second. I was going to split up, but we'll do it one step at a time. All over 2n, you with me? Now I'm going to split it into two fractions. So this fraction over this, the ends will go out and we'll get b squared over 2. Plus, this one over this one will still be b squared over 2n. Right? Now, that is just adding up n rectangles. We need to add up how many? Infinitely many. So we need to take the limit as n approaches infinity. So now, the limit as n approaches infinity of our sum, of our Riemann sum here, which was, just to be super clear, the limit of this thing is equal to, well, the limit of this thing as n approaches infinity. What is the limit as n approaches infinity of b squared over 2?
b squared over 2.
B squared over 2. And what is the limit of this as n approaches infinity?
0.
0. So the whole limit is b squared over 2. That's the area. Now, let me really test you here. I've got this right triangle. I tell you its base is b and its height is b. Question, what's the area of the triangle?
B squared over halves.
Half the base times the height. Or 1/2 b times b. Or b squared over 2. Okay, shocking. We got the area b squared over 2. Who saw it coming?
It's way easier.
Yeah, it's easier to just use your basic geometry for the area of a triangle. But the point of giving you the problem is so that you can validate it. Good?
Yeah.
Now, the next one that the author wanted us to do, well, now let me just, so you already know what the integral from 0 to b is of x, that particular one, right? That was equal to b squared over 2. Now I'm going to get really tricky. What is the integral from 0 to a of x with respect to x equal to?
A squared over 2.
Oh, goodness. You got it.
Alright.
Okay, now we're going to get tricky. What is the integral from a to b of x dx equal to now?
A squared over 2 plus b squared over 2? Or am I doing it wrong?
Is he doing it right or is he doing it wrong?
Yeah, big one.
Well, we could view this as the integral from a to 0 of x dx plus the integral from 0 to b of x dx, right?
Well, yeah, so A is. to the
Going
left.
from a to 0 and 0 to b is the same thing as going from a to b,
Oh.
right?
Okay.
Now that's 0 to a. We want the integral, we know the integral, this is a to 0, we know 0 to a. So I'm going to flop the bounds, which is going to make it negative. So this is equal to, I'm going to write the b one first, the integral from 0 to b of x dx minus the integral from 0 to a of x dx.
That makes sense.
And what do we get?
Negative
A squared over 2 plus
b squared over 2 minus a squared over 2. Intuitively, what is this saying? If I wanted instead to calculate the area of the seam
Oh, that's
from some starting point A to B, so if I wanted to calculate the area over here, how could I do it? Calculate the area all the way to B and then subtract the area to A.
Yeah.
There you go. That gets you the area from A to B.
Yeah.
But just showing you how you could get it just blindly using our properties as well. Good? Okay. Let's try another one. What is the integral from a to b of a constant equal to?
Let's just give me that constant. Or no constant.
constant times
A to B.
b minus a.
The constant times b minus a. Let's see this just to make sure it's completely clear.
Right, okay.
This is going to be the limit as n approaches infinity. What does a constant function look like? It looks like this. Boop, C. And we're going from A to B. So what is this area equal to?
You want to say something constant?
B minus A times C.
Yeah.
But let's write it out, all the nitty-gritty Riemann sum. So this is going to be the limit as n approaches infinity of the sum from k equals 1 to n of the height of the function at the point. What's the height of my function always?
C.
C times whatever our delta x sub k's are, whatever the bases are. We could have done the bases however we want. We can pull the C out, and then what is the sum of all my bases?
It's
Oh.
B minus A. So this is just going to equal the limit as n approaches infinity of, let's pretend that our basis here, we'll do a concrete number. Let's say that we were doing b minus a over n, whatever that was. We divided b minus a up into n pieces. You with me?
yeah.
So that's a constant, that's a constant. I'm going to pull all my constants out.
So important.
So this is the limit as n approaches infinity of c times b minus a over n times the sum from k equals 1 to n. I factored everything out, so I just have a 1 there.
Not 0.
No. If I have something like x and I divide it by x,
It's 1.
that's 1. Or if I've got an x and I'm going to factor an x out of it, then that is going to be equal to x. Factor out the x, we're left with a 1 there. Distribute back in, you've got x.
Yeah.
Okay, so that is a 1. What is 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times? N. So this equals n. The n's cancel out, and you're left with c times b minus a. Take the limit as n approaches infinity, and you're left with c times b minus a. You see all that algebra?
Taking n to infinity.
The n's cancel out. Look, you see that this whole thing right here is just the same thing as n. 1 plus 1 plus 1 plus 1 plus 1, n times is n. So this whole thing is just n.
Okay.
So now cancel out the n top and bottom, and what are you left with?
Okay.
C times b minus a. Now what is the limit as n approaches infinity of c times b minus a? C times b minus a. It's just a constant.
Yeah.
Good? All right. Definition of the average height of a function. So by definition, the average value of a function is just equal to, we already talked about this last time.
Yeah, we did.
What was the average height, do you remember?
The average height.
So if I've got some function here, and I want to know its average height from A to B, and imagine that I knew the exact area was A, how do I get the average height?
Integer times.
The idea was we find the rectangle that gives us the same area, and however tall that rectangle is the average height. You with me?
How does that give you an average?
Well, let's say that I've got some function here, and it has some area A from A to B. You with me so far? Okay. Now I want to know what's the average height of the function. That is going to be the height of the rectangle I can construct that has the same area.
Okay.
You with me?
Yes.
So that's what we're going to mean by the average height. Why average? It's going to be however tall this rectangle is that has the same area.
Okay.
If I know that the area of the rectangle is big A, how do I get its average height?
Big
No.
Big A divided by
You find
The
out.
area divided by the base gives you the
Oh.
height.
Yeah.
Base times height gives you area. So area divided by base gives you the height. So the average value of the function is going to be the area, the average height on some closed interval A to B is going to be the area divided by the base.
Yeah, so it's going to be A divided
So
by
it's going to be
A minus B.
1 over b minus a, there's dividing by the base, times the area, the integral from a to b of f of x with respect to x. That's what we mean by the average value of a function. The area divided by the base. Same concept. That's the average value of the function. Okay, so next we're going to calculate the average height of some function. Using that exact formula. Let's see. If I follow that, I think I'll be good. Okay, so in our next example, we are looking at the function y is equal to the square root of x squared minus 4, and we are looking for its average height on the interval -2 to 2. Sorry, I think I said x squared, but I didn't write it. X squared. Okay, first off, what is that the equation of? Talked about something like that a couple times. Let me square both sides, maybe that will help. We have y squared is equal to, oh my goodness, I wrote it backwards. 4 minus x squared. Sorry. 4 minus x squared. So then, this is 4 minus x squared. Or in other words, I get x squared plus y squared equals 4. Which is a circle with radius 2. Right? It's a set of all points whose coordinates, when you square them, gives you 4. Using the Pythagorean theorem, if I know here's my coordinates x, y, what is the distance here? from my center if that's right at the origin. What's the distance from here to here?
X squared plus y squared.
We can create a right triangle.
This is square root of.
So the distance of the base is x, the height is y. And what's the hypotenuse?
It's the square root of x squared plus y squared.
It's the square root of x squared plus y squared.
Yep.
So if I know x squared plus y squared equals 4, then the square root of 4 is 2.
What? Oh, yeah. That's right.
Just see, this is an equation of a circle. It's all the points such that when you square the x coordinate and the y coordinate and add them together, you get 4.
Yep.
The way that you see the equation of a circle is x squared plus y squared equals r squared, or this is r. And that's just the Pythagorean theorem.
I get you now.
Okay. So we are looking at y is equal to the square root of 4 minus x squared. Let's reverse engineer this and see exactly what this gives us. So I'm going to start right here with this is equal to 4. Let's solve for y. Move the x to the other side. So I get y squared is equal to 4 minus x squared. Take the square root, and I get y is equal to plus or minus the square root of 4 minus x squared.
Why can't you go 2 minus?
It's not the same.
Oh, yeah.
It's not, yeah, okay. So it's plus or minus. The plus gives me the top half of the circle. The minus gives me the bottom half of the circle.
Right.
Our function is this. So it is a top half of the circle with radius 2 centered at the origin. You see all that?
Yep.
So
Yeah.
draw out a quick picture of what we have. So let's start by drawing half a circle. I'm terrible at it. That's meant to be half a circle. This is a coordinate point 2. Here's 1. Here's -1. Here's -2. 1, 2. Here's our circle. We are trying to find the average height of that circle. How do we get the average height?
You take
One
the
over
area and then
one
times it by
side.
190 over
The average height is equal to the area divided by
the base.
the base.
Yep.
What is the area of this circle?
The area divided by base.
What?
No, what's the area of the circle?
It's the if you go from negative to 2.
What's the radius of the circle?
4. Or 2, sorry.
What's the area of the circle?
Oh.
How do we calculate the... Okay, here is a circle. Boop, radius r. What is the area of that circle?
Pi r squared.
Pi r squared. Holy cow.
My bad.
All right. We've got a circle here with a radius of 2.
Okay.
What's its area?
It's 4 pi.
4 pi would give me the whole circle, but we only have half of it.
So it's
So
4 pi over 2.
2 pi.
So it's just 2 pi is the area.
Oh my, that's so.
It's just, we are talking about the area of half of a circle with a radius of 2. The whole circle would have area 4 pi, just plugging in 2 for r. We have half of that, 2 pi. Okay, we back from La La Land?
Yeah.
Okay, 2 pi is the area. What's the base? 4. Whew. You had me nervous. Okay, so the average height then is what?
1/2 pi.
It's just pi halves.
4 pi halves.
That's the average height this thing achieves. What is pi halves roughly?
Oh,
About 1.5-ish. So the average height, if we were to try and draw it in right here, would be like this.
yeah.
Something like that. Good? Okay. So next, we did that. Okay, next is a theorem. This is called the mean value theorem for definite integrals. And we'll see why it's called that. So theorem, here's what we're going to prove. We are going to prove, I have it scribbled right here. We're going to prove that if f is continuous on some closed bounded interval a to b,
Some constant such that.
comma, then there must exist some point C such that the height at C is equal to the average height of the function. Or in other words, is equal to 1 over b minus a times the integral from a to b of f of x with respect to x. That's what we're proving.
Okay.
All right, so 1. Let f be continuous on the closed interval a to b, comma, and let little m equal the minimum value f takes on, and big M equal the max value f takes on. How do I know that f takes on a minimum and a max value?
Because it's continuous.
Because it's continuous. What theorem told us that? The extreme value theorem. So that is using the extreme value theorem. That's how we know little m and big M exists.
Yeah.
Because it's continuous.
Yeah, because it's continuous, and so on a closed bounded interval, it has to achieve some max and it has to achieve some min.
Even if it's a straight line.
Call that little m and big M. If it's just a straight line, then everywhere is a max and everywhere is a min.
Right.
But somewhere along the way, it has to reach a highest point.
Yeah.
Don't know why I wrote that somewhere. Okay. That is using the extreme value theorem. Okay, 2. Now what do I know?
You know that
What's the one property we took the time to prove?
6.
So using property 6 over here, I know that my integral can be sandwiched between those two values. So 2.
Oh yeah, that's right.
Then little m times b minus a is less than or equal to my integral from a to b of f of x with respect to x is less than or equal to big M times b minus a. And this was using property 6 that we proved over there, the one we actually took the time to prove. Okay, so now we got that. I'm going to divide everything by b minus a in that equation.
Okay.
Why?
Because it gets rid of it.
So then we get that m is less than or equal to 1 over b minus a times the integral from a to b of f of x with respect to x is less than or equal to big M.
Yeah.
You with me?
Yes.
Now, what is little m? It is the lowest value the function achieves. What is big M? It's the highest value the function achieves. What was the intermediate value theorem? Going all the way back. We don't have it written up. This is old stuff. If a function is continuous and it achieves two values, it achieves every value between them. In other words, if I know my function is continuous, and at one point its value is -3, and at another point its value is 5, then it had to be 0 somewhere in between. It had to be every value in between, but
Yeah.
0 as an example. So, I know that my function achieves little m at some point. I know it achieves big M at some point. And I know this is a value between those two. So then that, comma, and so by the intermediate value theorem, comma, there must exist some point C in my interval such that f at C is equal to 1 over b minus a times the integral from a to b of f of x with respect to x, right? That value is between my minimum and my max value. So my function, there has to be a point in my function where its height is that exact value.
Yeah.
Because at some point it's little m, and at some point it's big M. So at some point it's that value, because that's between little m and big M.
Yeah.
That's it. That's what we were trying to prove.
You saw number C.
If f is continuous on AB, then there exists some C in this closed interval such that the height at C is equal to that point.
So you're saying there's some C where
You
it's
just
the
use
average.
that.
Yeah, there's some C that gives us the average height of the function.
Could you have just used the intermediate values theorem and just say there was?
That's what we did. We just had to sandwich the value between two heights of our function. That was the only thing we had to do. Here's what we already had. Now, manipulate to make that value between two heights of our function. And we're done. So it just easily follows from the their intermediate value theorem. And that is why it's called the intermediate value theorem for definite integrals. Because you're basically just redoing the exact same thing. Okay, yep. Now the name makes perfect sense, right?
Yeah.
Okay. Special case. Proof. If I know that the integral from a to b of f of x with respect to x equals 0, then there exists c such that f at c is equal to 0.
Isn't that just directly?
It's directly using what we have right here.
Yeah.
Oh, yeah.
So 1, by the above theorem, comma, there exists c in that interval, in that closed interval, a to b, such that f of c is equal to 1 over b minus a times the integral of f of x with respect to x, right?
Where do you get that?
That's just using this theorem. This theorem says there's a c such that's equal to that. So there's a c that's equal to that. What is the integral from a to b of f of x with respect to x?
What was it?
There.
Or
0.
It's 0.
Yeah.
So that is equal to 0. So that gives me that f of c is equal to 0. So there was some point c such that the height of c was 0. If the average height of the function is 0, then there's a point where the height is 0.
Right, so, okay.
It's just a simple use case of this theorem.
Alright.
Just one special use case where the average height happens to be exactly 0. Or sorry, where the area was 0. If the area is 0, then the average height is 0. That's what that was saying. Okay. Next, we are ready to start the fundamental theorem of calculus. So, what is a fundamental theorem of calculus? Before we do this theorem, let me introduce you to some notation. Well, I guess I can write it in the theorem too. Theorem. If f is continuous, we always need our function to be continuous, on AB, and big F of x is equal to the integral from a to x of f of t with respect to t, comma, then f prime of x, the derivative of it with respect to x, is just equal to little f of x. Okay, this is a little bit weird. What it's telling us is that taking the integral of a function and then taking its derivative gets you back where you started. In other words, it's saying, let me write it out a different way. The derivative with respect to x of some integral from a to x of f of t with respect to t is just equal to f of x. Taking the integral of a function and then differentiating what that integral gave you gets you back where you started.
Yeah, I see.
Get you back to little f. That's what it's saying. So before we do this proof, let's do some concrete examples just to get you comfortable with what it's saying. Because I know that notation is weird to you. It's scary to see something like that. A function whose output is what? Notice that the x is right there and the x is right there.
Oh, weird.
So yeah, let me first give you intuition for what this f is.
Okay.
So here I'm going to draw out, this is going to be our t-axis. And here is going to be some function, little f of t. Good so far?
Okay.
Here is some point A, doesn't matter where. Now, big F gives me the area from A to some point X. So pick some point X here. then this area is what we mean by big F of x. It's the area from A to x.
Okay.
You with me?
Yes.
Now, intuitively, what this is saying is that the derivative of an integral gets you back to your function, right? Let me write that one more time right here. Intuitively, this is saying the derivative with respect to x of the integral from a to x of f of t dt is just equal to f of x. Let's get intuition for that. This is saying the change in your area is just the height of the function. How is this function changing? How is the area under the curve changing right here?
Height.
It's related to the height. If my function is shooting up, it's getting very tall, then the area is jumping up. If my function is shooting down, then the area is growing slowly. If my function was 0, if my little f came down and it was 0 right at x, then at x, my area isn't changing at all.
Oh, right.
So intuitively, what this is saying is that the change in your area is just the height of a function. The same way that the change in how your function is growing is just the slope, the change in how the area, the change in the area under the curve is just the height of the function. Tall function's area is increasing fast. Small function's area is increasing slowly.
Yeah, but can you also just increase the base?
Well, we could go further, but how is the area changing right at the point x?
The only way.
Yeah, it's changing by adding that height of the function at the point x.
Why can't it go left more?
Well, just right at x. How's the area changing?
Up.
It's changing by the height of the function at x. It's like we're adding this little area if you include the point x under your curve. You with me?
Yeah.
That's intuitively another way that we can try and think about this. The change in area of a function at a point is the height of the function at the point.
Okay.
Just intuition. Now, before we actually prove this thing, let's do some concrete examples. So, first one I want you to do is calculate this for me. What is the derivative with respect to x of the integral from a to x of the integral from a to x of t cubed plus 1 dt? What is that derivative with respect to x? What this formula is saying is that if f of x is equal to some integral like that, then the derivative of it is just plugging in x to your function.
It's x cubed.
So in this case, it is just x cubed plus 1.
Well, why even bother with e?
Oh.
It's just a dummy variable.
Yeah, why have it instead of x?
Because I can't call this f of x if I'm using x to talk about how far over we're going. I just need different variables.
Okay.
So I could have called this one f of t and did the integral from a to t of f of x dx. And then t would be this point and this would be the x-axis. So I either got to call this the t-axis and that x, or call this the x-axis and that t. Doesn't matter which way we go.
Okay.
But so that is what the formula is saying. The derivative undoes the integral. And so it's just like plugging x into whatever your function was. You with me? Let's try another one. Let's scoot that over. X cubed plus 1. Okay, let's try another one. We're going to do the derivative with respect to x of the integral of, what's our next one? X to 5 of 3t times the sine of t dt. What does that equal to?
3 times x times sine of x. Isn't it?
Well, be careful. This says f prime of x is equal to f of x, where f of x is from a to x. It has our variable up there. This one, our variable's down here.
So it's negative of all that.
So it's going to be, tell me what it is?
Negative 3t times sine of t.
Negative 3x times the sine of x.
Alright, x, yeah.
That's all there is to it.
What about your 5?
The constant there doesn't matter. Why doesn't that constant there matter? Intuitively, what you're doing is taking an integral then a derivative. Let me give you some intuition for this from what we already know. What is the antiderivative of x? You've already been doing that. What's the antiderivative of x? That's x to the 1. What's its antiderivative?
X squared over 2.
X squared over 2. X squared over 2
Over 2.
Plus c.
plus some constant.
Yeah.
Now take the derivative of that, and what do you get?
Yeah, X.
You get back to x.
Oh.
And that constant doesn't matter. That's what that little a is giving you, or what that 5 is giving you. It's giving you a constant that ends up not mattering. Good?
Yeah.
Okay, so that's why the constant didn't matter. And then the negative just comes from the fact that we swapped it.
Yeah.
Yeah.
Okay, let's try another one. See if you can do this one all in one go. What is the derivative with respect to x of the integral from, oh, this one's kind of hard, 1 to x squared of cosine of x, or of cosine of t dt.
What?
Okay, now we're taking it, but our integral is going to x squared.
Is it those?
How on earth do we find the derivative of that with respect to x?
You bring the 2 down. So it would be 2 cosine t. Or
2
x.
cosine of X. Is that what?
Well, if this is what f of x equals, big F of x, right? This is what big F of x is equal to, right?
Yeah.
Well, actually, that's what big F of x squared is. You're plugging in x squared is what you're going to, right? What I'm going to do is let u equal x squared. And now f of u
Oh, I see.
is just equal to the integral from 1 to u of the cosine of t dt.
Which is equal to cosine of U. Which is equal to cosine of I squared.
Except for it's negative.
Well, now we need to take the derivative with respect to x.
We should know what x.
Okay, cosine of U.
So the derivative of f with respect to x is the same thing as the derivative of f with respect to u times the derivative of u with respect to x. It's a chain rule.
Yeah.
So we'll calculate the derivative of that with respect to u, and then multiply that by the derivative of u with respect to x. So what is the derivative of this with respect to u then?
It's cosine of U.
That is just cosine of u,
Okay.
and then we need to multiply by du dx.
Which is 2x.
And so this is all equal to now cosine of u, remember u is the same thing as x squared, times du dx.
Sweet.
Just a chain rule.
Yeah.
Okay, I think that was it for those examples. Good?
Yeah.
Okay, so with those examples, let's actually prove this thing. We'll just start down here. So one, let's see. Let f be continuous on AB, comma, and let big F of x equal the integral from a to x of little f of t dt. Good so far?
Oh, I forgot we're proving that. Yeah.
Yeah, we're starting to prove. 2. So now I need to figure out what the derivative of f is.
Yeah.
I'm trying to show that the derivative of big F is just little f. That's what I'm trying to show. So let's calculate the derivative of big F. What is the derivative of big F? By definition, what is the derivative of something?
It's the limit.
It's the limit of the difference quotient as the denominator goes to 0. Reminding you way, way back. The derivative with respect to x, dy dx, or we'll say of f. The derivative with respect to x of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x
Over H.
all over h. Remember that definition going way, way back?
Yes.
Yeah, I do.
It's the limit of the rise over the run.
Isn't that rate of change?
Yeah,
Yeah.
Yeah.
derivative. So that's what we want, the derivative of this thing. So the derivative of this thing is going to be the limit
X.
as h approaches 0 of
F of x
I'm going to pull the one, well, first I'll write it that way, and then we'll go do it as we go. F of x plus h.
Not big F.
Yeah, I'm calculating the derivative of this thing.
Oh,
The derivative of this is plug in x plus h minus what you get when you plug in x all over h.
Yep.
You with me?
Yes.
yeah.
Now, we'll take our limit here in a second, but just rewriting the inside.
You can't get
Rewriting the inside, we'll pull the 1h out front rather than dividing by h. And now I'm going to multiply 1 over h by this thing minus that thing. You with me?
Yep.
So 1 over h. What is f of x plus h? What is this piece? That is the integral from a to x plus h of f of t dt. That's exactly what f of x plus h is. It's when you plug in x plus h to this function. Replace your x with x plus h. That's how you plug x plus h into big F, right? And then we're going to subtract what we get when we plug in x. So from a to x of f of t dt. Now what is this? This gives me the area from a to x plus h. Now I subtract away the area that I get from a to x.
Pretty good.
And what portion am I left with?
The area from A to H.
Not quite.
Uh-oh.
Let me draw a picture of this. Here's x.
Okay.
Here's x plus h.
Oh, you have the area.
Here's the integral from a to x.
Uh-huh.
Here's the area from a to x plus h. I'm doing a to x plus h minus a to x, and what am I left with?
You're left with the area
I'm left with this sliver,
Which
of x to x plus H.
which is from x to x plus h.
Right.
So this is equal to, we still have the 1 over h here, but now the difference of these two integrals is just the integral from x to x plus h of f of t dt. You with me?
Yep.
And we still haven't taken our limit yet, just reevaluating the inside.
Okay.
So I just rewrote my difference quotient. This is the same thing as this.
Yeah.
Yes.
Yeah.
Yep.
That makes sense.
Good so far? Okay. Now, notice what this is. This right here is the area of this rectangle.
Yeah.
What is h?
The difference there.
The base of the rectangle.
Base. Yeah.
So I have the base of the rectangle times the area. What does the base of the rectangle times the area give us?
The average.
The average height.
Yeah.
So 3. By whatever this theorem was,
Yeah.
so by that guy over there, we didn't name it, so I can't call it something, Theorem 8 or whatever it is in your book, we know that by that there must exist C in this base, in x to x plus h, such that f of c is equal to our average height, 1 over h times the integral from x to x plus h f of t dt. Okay, mouthful. But you see how that is from that theorem? There has to be some c in this interval, c is somewhere like right here, such that the height of c gives us the average height of the function. Good?
Yeah.
Okay, so by that there exists this, comma, and observe, what is the limit as h approaches 0 of c equal to?
That's just C.
Limit
As h goes to 0, what happens to this interval?
goes to 0.
Goes to smaller.
It gets, what? It goes to x. That c has to get closer and closer to x.
Oh, yeah.
You with me?
Yes. Yes.
So the limit as h approaches 0 is the same thing as the limit as c approaches x. So let's put all this together. 4. So then we have, remind us what we started with. We're looking for this thing. F prime of x is equal to the limit as h approaches 0 of this thing, which is the same as this thing, which is the same as this thing, which is the same as this thing, which is f of c for sub c in that interval. So it's the limit as h approaches 0 of f of c. But that is the exact same thing as the limit as c approaches x of f of c. As h approaches 0, c approaches x. So the limit as h approaches 0 is the same thing as the limit as c approaches x. You with me? And what do we know about f? It's continuous. What is the limit as x approaches, or as c approaches x of f of c? It's kind of backwards. You're used to x approaching c instead of c approaching x. But what does it mean for a function to be continuous?
That means that it's equal to the value of the function.
Every limit is equal to.
The limit of the function at a point is equal to the value of the function at the point. So what is the limit as x, or as c approaches x of f of c? It's just f of x. Da 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 da! Confetti! We did it. F prime of x is equal to little f of x. As h gets closer and closer to 0, the area of this function basically just turns into whatever the height of the function is. Or the area that we're adding is basically just the height of that function. Intuitively what it's saying, some geometric way of trying to read it. Okay. Oh, sorry, go ahead.
Why don't we just try and define integrals as like antiderivatives and then have that be a given thing?
We use antiderivatives to get this next part of the theorem will explain your question. If it doesn't, let me know.
Okay.
So this is what we call the first part of the fundamental theorem of calculus. We gotta do part 2 now. What is part 2? Theorem. Let f of x be any antiderivative of little f of x. So let big f of x be any antiderivative of little f of x. Then the integral from a to b of f of t with respect to t, same function, just different dummy variable.
Okay.
We can keep it x this time, doesn't matter. It'll be better to use t there, just so we don't get confused. So then the integral from a to b, no, let's keep it x. Here's how you're going to see it. Sorry. Doesn't matter though. The integral from a to b of f of x with respect to x is going to be our antiderivative at the point b minus our antiderivative at the point a. This is how we will actually calculate integrals. We will not calculate them by hand. This is a formula that we use to calculate definite integrals.
Sweet.
And notice what it says. Let f of x be any antiderivative. So an integral doesn't give you the antiderivative. We can use antiderivatives to calculate integrals.
Oh, I see.
It's kind of like a product isn't an area, but we use products to calculate areas. You can kind of think about it like that. So we use antiderivatives to calculate integrals. And now I'm going to prove that you can pick any antiderivative of that you want, and then use it to calculate the integral of that thing. Alright, so 1. Let f of x, oh, we already said that right there. So we already know that f of x is an antiderivative of little f of x. So instead what I'm going to do is let g of x equal the integral from a to x of f of t dt. So let g be the integral of whatever that thing is up to some point x. You with me so far?
Yeah.
Question, what is the derivative of g of x?
Is that
It's just f of x, right?
right? Yeah.
That's what we proved up here. Right? If f is the integral, then Oh, we wrote it clear here. If f is the integral, then the derivative of f is just that inside function. You with me?
Yeah.
So the derivative of g is just
Oh, yeah, we did.
little f.
Yeah.
Now, if the derivative of this is that, then the antiderivative of this includes, it is an antiderivative of little f. That's what we know about g so far, is it is an antiderivative. Which one, we don't know, but it is an antiderivative. Good so far? So let g be that, and observe that f of x is equal to g of x plus a constant. All antiderivatives of a function differ from each other by at most a constant. This was one that we already proved going back a little bit, but give you the intuition for it really quick here. What is the antiderivative, once again, of x? What's the antiderivative of that?
X squared over 2 plus c.
One is x squared over 2 plus 7. Another one is x squared over 2 minus 19. All antiderivatives differ from each other by at most a constant. Okay, so whatever, so g of x is an antiderivative, f of x is any antiderivative, we don't know which one. But whatever it is, these two differ from each other by at most a constant. Or in other words, move g to the other side, f of x minus g of x is a constant. So f of x is equal to g of x plus c. Good? Okay, 2. Then let's calculate f of b minus f of a. What is f of b minus f of a equal to? Well, that's going to equal to, plug b into this, what do I get?
G of B plus C.
G of b plus c. Now subtract what I get when I plug in a.
Same thing.
So minus g of a, and then minus c. You see that?
Why?
Because we're subtracting what we get when we plug a into this.
So I get to 2c.
So why is the C negative? Oh, yeah, gotcha.
You see it now? You're just distributing the negative over that when you plug it in. Okay, and so the c's go out. And notice that this is equal to g of b minus g of a. Which is equal to, what is g of b? Look at g's definition.
So it says a goes to b.
It's the integral from 0,
0.
sorry,
From
A.
A to X.
there's two different ways to do it. Another one is we could start at 0, but I chose a, it doesn't matter.
F of T.
F of t dt minus now g of a, which is the integral from a to a of f of t dt.
0.
And that one's 0.
Yeah.
Why?
Because a goes to a, 0.
A goes to a. What's the area going from a to a under f?
0.
So I'm going to start at a. Let me go all the way over to a. What's that area?
0.
0. So this term is just 0. And so it is equal to just the integral from a to b of f of t dt. So we can use any antiderivative we want to calculate an integral. Pick one, any one, doesn't matter.
Oh.
That's what we just showed. Good?
So you can pick any antiderivative.
You can use any antiderivative you want to calculate an integral. We choose the antiderivative where the constant's 0.
So can we do quick examples of that?
Yes, we're going to do some examples of that. So let's calculate some integrals now. So our first one, let's calculate the integral from 0 to pi of the cosine of x dx. First, we need to find an antiderivative of cosine.
Which is
What is a function such that when you take its derivative, you get cosine?
sine.
Sine. So this is going to be sine of x. And now we need to, here's common notation. We need to evaluate it from 0 to pi.
Yeah.
What that means is, this is equal to sine of what you get when you plug in pi minus what you get when you plug in 0.
Really?
Notice that that's what this says. The integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a.
Oh, that's so
Your
easy.
area up to b minus your area up to a. Another way you can think about it.
Oh, that's so cool.
Okay, and so what is the sine of pi?
Is it sine
Oh, yeah, sorry.
Sine of 0 is 1.
It's
What is sine of pi?
0.
Come on, trick boy.
Sine of
0. Mine is 0, and the answer is 0. Okay, why is it coming out 0? Let's graph sine of pi really quick.
Oh, because of the negative area.
Yeah, sine of pi starts out at 0, and we're going whoop, whoop.
Yeah.
Right?
Yeah.
So, did I do that right? No, we're not graphing sine, we're graphing cosine. That's way wrong.
Oh, yeah, that's right.
Oh, yeah.
We're calculating the area of cosine from 0 to pi. Cosine starts out up here at 1, and then it comes down to 0 pi halves, and then it goes like this. Here's pi. So it gives you as much area above the curve as it gives you underneath the curve.
Which is 0.
And so it adds up to 0.
Oh, that's what it's saying.
Notice, let's instead do our integral to pi halves.
Then it's.
Then our area better come out something, so let's do this again, but pretend it was pi halves. Our antiderivative is still sine, but we do pi halves. And now this is pi halves minus 0. And what is the sine of pi halves?
Root 2 over 2 or.
What is the height at pi halves?
1.
1. The height at 90 degrees, 1. Minus 0 is equal to 1. So this area is exactly 1
Oh, yeah.
on the sine function. Make sense?
Yeah.
Okay, let's calculate another antiderivative. Secant and times tangent, is that what it was? Yeah. So the integral from negative pi fourths to 0 of the secant of x times the tangent of x with respect to x. Now we're looking for something whose derivative is secant times tangent.
That's just
Go.
That is just secant. So this is equal to secant of x evaluated from minus pi fourths to 0,
Yeah.
which is equal to secant at 0 minus secant,
Wait, other way around, isn't it?
the end point minus the start point,
Oh, my bad.
b minus a. Where do we have it? Right here.
Oh, right, okay.
Top minus bottom. Times the secant of minus pi fourths. Okay, what's this equal to? Secant at 0. What is secant? Remind you, it's 1 over cosine. So what is cosine at 0?
0. Undefined.
Cosine is 0.
What's cosine at 0?
1.
What's your x coordinate at 0 degrees?
1. 1.
Oh, 1. That makes
1.
sense.
Okay. And then 1 over 1 is
1.
1. Okay. Now, if we go down pi fourths, what is your x coordinate?
Negative. Or
It's going to be positive because we're still on the right side.
3 over 2.
root 2 over 2 is
Root 2 over 2. So root 2 over 2 is a cosine. Now we need the secant, which is the reciprocal of that. What's the reciprocal of 2 of that?
2
over
2.
So we can call that 2 over the square root of 2, but what is that?
Rationalized. Root 2.
Yeah,
Root
2
2.
root 2 over 2.
That's root 2.
It's just root 2.
What?
Times root 2.
So 2 is the same thing as the square root of 2 times the square root of 2.
Oh.
So we have 2 over the square root of 2. What does it equal? Square root of 2, cross out the square root of 2 top and bottom. Or however you want to think about it. So this is 1 minus the square root of 2. Let me just make sure I'm not making any mistakes on these. I don't even know where these examples are. 1 minus the square root of 2 over 2. Or square root of 2. Okay, we did that right. And then last one, example. Now, we are going to calculate the integral
Of 1 to 4.
1 to 4,
3 over halves.
3 halves the square root of x
Minus 4 over x squared.
minus 4 over x squared dx. Okay,
What do? We find.
calculate the antiderivative of that.
So 3 over 2.
Maybe help you think about it a little bit better, that's the same thing as 3/2 times x to the 1/2
I was just getting there.
minus 4 times x to the minus 2.
Yeah.
So when we take the antiderivative, what do we do first?
We put the thing, we add
We add
one,
one.
put it on.
Add 1, so that gets us to 3/2.
And then put it on the bottom,
And then divide by 3/2 or times 2/3.
Which cancels out.
which cancels out. Because you
And then for this one, what are we going to do?
you add one, so.
Which will make that a -1. And then divide by -1 will make that a plus.
Gotta make it 2.
No. You
Oh,
divide by,
you're right.
divide by.
Divide, add 1, then divide.
Oh.
Okay, so that is just going to be, those cancel out, and we're left with
X plus.
x to the 3/2 plus 4 over x
Oh, that's good.
evaluated from 1 to 4.
Now, look, 1.
So plug in 4 first, and then minus what you get when you plug in 1.
4. that's
So
4.
4, what's the square root of 4?
2.
Cube it,
8.
8,
Is that how you do that?
yes.
Yes.
Plus 4 over 4 is
4.
1. So that's what we got when we plugged in 4. Now minus what we get when we plug in 1. What's 1 to any exponent? 1. And what's 4 divided by 1? So we got 9 minus 5 is equal to, and double check, 4. Okay, so we did all that right. Let's see, couple more examples, just 3 more examples and then we're done. So we've covered all the theory we need, but just want to make sure you have plenty of examples.
That's fun.
Good enough. Okay, so our next one, we're told a velocity function. So our velocity function v of t is equal to 49 minus 9.8 t, and this is meters per second. So what happened was, we launched a ball straight up in the air. It shot off at 49 meters per second, but now gravity keeps slowing it down, slowing it down, slowing it down, and eventually it's going to fall. We were asked to find the displacement and then the total distance after 8 seconds. So it shoots up in the air. We're looking at the total displacement and then the total distance. What is distance versus displacement? Just to give you intuition. I start here at x equals 0.
Total displacement.
I walk 3 meters, and then I walk back 2 meters.
So if I-
My displacement is 1 meter. I'm only 1 meter from where I started. My total distance is 5 meters.
Yeah.
Similarly, velocity versus speed. If I'm walking this way at 1 meter per second, and then I'm walking this way at 1 meter per second, my velocity went from +1 to -1. My speed was always just 1. So speed is the absolute value of velocity. Distance is speed times time, not velocity times time. You use velocities to calculate displacements. You use speeds to calculate distances.
Yep.
Or in other words, so if s of t is our displacement function, then this is going to be the integral of our velocity. And then if d of t is our distance function, it is the integral of the absolute value of velocity. We never want to subtract values just because you were walking backwards. That's the difference between those two. You with me? So we're going to calculate first the displacement, and then second the distance.
Displacement requires subtraction.
Well, the fact that the velocity changes already tells us the displacement changed, and so we're fine. We don't need to keep track of that. Here's how we're going to calculate displacement. We're going to integrate velocity. Here's how we're going to calculate distance. We're going to integrate the absolute value of velocity.
Okay.
We're going to integrate the speed.
Yeah.
Make sense?
Yep.
That's intuitively how we're going to do this. Okay, so first of all, s of t, our position function, is just going to be the integral of this with respect to t. So the integral from 0 to 8, because we're doing it over 8 seconds, of our velocity function. Right? What does that equal? So let's integrate this. What's the integral of 49? well, t in this case, but yeah.
Or we're gonna keep.
So we got 49t minus, it's going to be t squared then divided by 2, right?
Yeah.
What's half of 9.8? What's half of 8? What?
4.9.
4.9. So 4.9 t squared. What's half of 98? 49. Okay. And we're evaluating this from 0 to 8.
So what do you get when you plug in 1?
And so what do we get when we plug in 8? Someone pull out a calculator. We're not going to calculate this by hand. Just do 49 times 8 minus 4.9 times 64.
4, 9, times 64.
So 49 times 8 minus 4.9 times 64.
It's 78.4.
And we can pull this out to make sure we're not making a mistake as we go. Where are you?
Where are you?
You said 78.4?
Yeah.
You didn't mess up.
Did not?
You did not mess up. Or both you and the author did mess up. Okay.
And then
Now.
the other one is 0.
Huh?
And then evaluate it at 0.
Right, and then plug in 0 gives 0. So the answer is just 78.4 meters. So after 8 seconds, the object is 78.4 meters in the air. But after 8 seconds, it's already gone up and then started coming back down.
Yeah. Right.
So now we want to calculate the distance it went. You with me?
Yes.
And so we need to see where the velocity is positive and where it's negative.
So that is our critical points.
Sure, that's one way that we could do this. So we've got 0 here, we've got 8 here. I need to figure out when the velocity switches from being positive to negative.
Yeah.
When is the velocity 0? What time makes it 0?
0. Wait. What is it? Oh.
You can see it.
Is when t makes. It's when
Yeah,
t
what value of t makes
5.
5?
What?
Because half of that is 4.9. Divided by 2 times 10 gets you that.
Oh.
Oh,
So 5.
That was wrong, obviously.
So the velocity is positive from 0 to 5, and the velocity is negative from 5 to 8.
How do we know that's negative necessarily?
Well, plug in 5 makes it 0. Plug in a value bigger than 5 makes it negative. A value smaller than 5 makes it positive. It's a linear function, so it only crosses the x-axis once.
Oh.
Okay, so then our distance function, our distance up to time t, is equal to, we're going to do the integral from 0 to 5 of our velocity function. And then we need to minus the integral from 5 to 8 of our velocity function. Because our velocity is negative on this interval, so negative makes it positive. You with me? And that's how we're going to calculate it. So this is going to be equal to, the antiderivative is still just the same thing. So we're looking at 49t minus 4.9t squared. Evaluate that from 0 to 5. And then once you get that value, subtract 49t minus 4.9t squared, evaluated from, maybe you put the evaluation inside the parentheses, let me know, evaluated from 5 to 8.
Yep.
And so, let's see, what do we get when we plug 5 into this thing? 245 minus whatever.
The 122.5.
122.5 minus what we get when we plug in 0. Okay, we don't care.
Which is 0.
Now minus, what do we get when we plug in 8?
78.4, right? First.
Ooh, make sure you're plugging in for both of them.
Isn't that what we got for?
No.
Here. Wait. Oh, my bad.
Yes.
Yeah, it's
Yeah.
78.4.
Because
Okay.
4019.
Yeah, it's 78.4.
78.4. Sorry, minus 122.5. What we get when we plug 5, right? And so now we just need to know whatever that difference is and then add to that. Keep going. So
That's 122.5.
you could just do that minus that plus that if you want.
Plus what?
You could do this minus that and then plus this.
Okay.
However you want to do it. And let's see what the book says. Make sure we didn't make a mistake. Mark B. 166.6.
What I got.
And that's what the author got. 166.6. Okay, so there's the distance it traveled going both up and down
After 8 seconds.
after 8 seconds.
Sweet.
Make sense? All right, the next example is to find the area between two curves. So, one of our curves is
Negative.
4 minus x squared. So 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 3, 4. See if I can draw this half decent. So 4 minus x squared is a parabola upside down starting at 4. So that is going to look something like this. You with me?
Yeah.
And then the other one is x squared minus 4. So this one right here is 4 minus x squared. And then x squared minus 4 is a parabola pointing up starting at minus 4 right here.
We're trying to find the area in between them.
And so we are trying to find this area.
Is that 0?
The area.
Yeah, it's an area 0.
Now,
What? Oh, I guess we're not. Okay.
area is always a positive number. We never defined area. I forgot to write that. The area, you can think about, the area is equal to the integral from a to b of the absolute value of f of x dx. Okay, there's area.
There you go.
Yeah, I was thinking of the
The
x-axis.
displacement of that would be 0.
Positive and negative like the sign. But we're not doing the same thing.
Now, so we're going to calculate the area between these two curves.
Okay.
We understand what we're trying to do?
Yeah.
Now, the integral from, notice that they go from -2 to 2. That's where they cross the x-axis.
Yeah.
Plug in 2 for that, you get 0. Plug in -2 for that, you get 0. This one down here, this was 4 minus x squared. Again, plug in those two values, those are your zeros.
X squared minus 4, isn't it?
Yeah.
Oh, sorry. Thank you. And 4 minus x squared. Right?
Yep.
So, the area underneath this curve is just the integral from -2 to 2 of 4 minus x squared. Right? That would give me the blue portion. Now, if I do plus the integral from -2 to 2 of x squared minus 4, notice that all the area is under the curve, and so this is going to spit out a negative number. And so if I just subtract it, then that will give me the actual area.
Yeah.
That's one way to do it. You with me?
Yeah.
This, using our properties, the difference of the integrals, so the integral of f of x minus the integral of d of x is just the integral from -2 to 2 of f of x minus g of x. So a 4 minus x squared minus this thing, so minus x squared plus 4. With me? Now notice what that is doing, pictorially, is we're saying our height is going to be this function minus this function. The top function minus your bottom function gives you the distance between those two. Intuitively, what you can think about this as, so this right here is giving you the height, it's doing the top one minus the bottom one, right? That's what this is. That's doing this minus this. The top function minus the bottom function at a point, this value minus this value gives me the distance between them.
Yeah.
one of the ways we read integrals is this is our height, and we're doing it for each infinitesimal small dx. And we're doing an infinite sum of them. So we're doing an infinite sum of our heights times our widths. And that's one way that we think of an integral. So here's our height for each slice. Here's our width of each slice. Do an infinite sum from -2 to 2, and that gives me the area. And now we can calculate this integral. Let's just simplify really quick before we calculate. -2 to 2. 4 and 4 is 8. Negative and negative is -2. So 8 minus 2x squared. You with me? Same thing. And now let's take the integral. What's the integral of just 8?
It's just 8x.
8x. And then this one, plus 1 divide.
It's x to the 3 over 3. Actually, x to the 3 over 2.
So
2x.
2/3 x cubed.
Yes.
Right? That's a minus sign.
Yeah.
And now we need to evaluate this from -2 to 2. So plug in 2 and then subtract what we get when we plug in -2. So plugging in 2, I get 16 minus 8 times 2 is 16/3. So that was plugging in 2. Now I need to subtract what I get when I plug in -2. Use parentheses so I don't forget to distribute my minus. -2 times 8 is,
-16.
and then -2 cubed is, -8 times 2/3 is going to be minus 16/3, or plus actually, because that's minus,
Right.
and we're doing -2 plus. You with me? Which is equal to, we get 16 minus 16/3, minus minus is plus 16 minus 16/3. Which makes good sense. 16 minus 16/3 is going to give me this area, and then this 16 minus 16/3 is going to give me that area.
Yeah, that makes sense.
Or actually, it's probably doing that half and that half. I don't know. Either way, this is equal to, we've got 32 minus 32/3 is one way we could think about it if we wanted. Right? Which is equal to,
Times 8.
how many thirds is 32?
Oh, how many thirds is 32?
10 and 2/3.
Well, let's just keep it thirds. So it's going to be 96 thirds. Now minus 32 thirds leaves me what?
4 thirds. That's got it.
That is a power of 2, not a 3. Prime factorization. Let's double check. Oh, that's the wrong one. Where is it? We did that. Find the area in the region bound by the graph right there, and that's not it. Oh, example 6, there it is. Thirty-two thirds, add them up. So he just didn't add them up. He calculated each one separately. 64 thirds, which is what we got. Okay, so last example, we are trying to find the area between that curve, x cubed minus 2x squared, whatever. Someone read it to me.
X cubed minus x squared minus 2x on the integral.
Sorry, x cubed what?
Minus x squared.
Okay.
Minus 2x. On the integral, on the closed interval, -1 to 2.
Okay, and just to give you a brief idea, let me very roughly sketch the picture from the book. What this thing looks like. So this thing roughly looks like something like that, where that 0 over here is 2, and over here is -1. So we're going to have some portion that's a positive area and some portion that's a negative area. We need to calculate the total area. So we're trying to calculate this area right here.
The total meaning you subtract it from the big one.
Well, we just want to calculate what's all that area. It's just when we calculate this integral, it's going to spit out a negative number.
Yeah.
Now there's no reason for you to have known that it was necessarily going to look like this. Let's really quick see that from the function. So our f of x is equal to, factor in x out of all that, and we get what is left?
X squared minus x.
X squared minus x plus 2. Okay, let's factor that again. How do we factor this? Two numbers multiplied together give me 2, added together give me negative 1.
Negative 2 plus 1.
Negative 2, and then x plus 1. So this function is 0 at positive 2, and at negative 1. At 0, at negative 1, and at positive 2. With me?
Yeah.
Now we would need a test on which intervals is it positive or negative. So we know that across at negative 1, at 0, and at 2, we need to figure out is it positive or negative in each of those places. So from negative 1 to 0, pick a number, 1/2, plug it in. 1/2 is positive. 1/2 minus 2 makes it negative and positive.
Positive.
You're trying to see there.
Oh,
What am I
okay, you're
doing?
supposed to do negative 1/2 because you're between negative 1 and 0.
Thank you. We're plugging in negative 1/2. Good. Yes, 1/2 makes it positive. Negative 1/2 gets us a negative, and a positive. Negative times positive is positive. And now when you plug in 1/2, as we were saying before, that gives you negative. So my function is positive from here to here, negative from here to here. So if I want to get this area right, the area, I need to take the integral from negative 1 to 0 of f of x. And then I need to subtract the area from 0 to 2 of f of x to get the area. Because I know that the integral is going to spell negative numbers over here.
Yeah.
Good?
Yep.
And now we just calculate that for this function, and that's all there is to it. So, really quick, what is the antiderivative of this thing? So we'll just call that big F really quick. What is big F of x?
4x divided by 4 minus 2x over 2 plus
X to the 4 over 4 minus what?
X to the 3 over 3.
X cubed over 3.
plus
Plus x to the 3 over
x.
Just
squared.
x squared,
Yeah.
right?
Yeah.
Yeah.
Okay, so now this integral, this piece is going to be equal to what we get when we plug in 0 minus what we get when we plug in negative 1. So plug in 0, what do I get? 0. Now I need a minus what I get when I plug in negative 1. Plug in negative 1 to that, what do I get? We'll just write it out. 1/4
Minus negative 1/3, or
minus a third.
should be negative 1/3.
Yeah, so it'll be plus,
Oh. Huh. Yes, because it's a minus and a negative. You're right. Make sure you're doing that right. 1/4 plus a third
plus
Plus 1.
plus 1. All right, that will give us this portion. Let's really quick figure out what that is. What's a fourth plus a third? Or 3/12 plus 4/12 is 7/12 plus 12/12 is 19/12. Hopefully we did that right. So 19/12, that's the area of this portion, right?
Okay.
Now we need to calculate the area of this portion.
Uh-huh.
So to calculate the area of this portion, we need to evaluate this thing from 0 to 2, and then make it negative.
0, 0, 2.
Or we could instead think about it as the integral from 2 to 0 of f of x dx. And then we don't need to worry about the negative. Makes no difference, I bet. We'll keep it like this. So we're going to subtract now what we get when we plug 2 into this thing. So plug 2 in, what do I get?
1/2 to the 4.
No, plug 2 in. 2 to the 4 is 16 over 4 is
4.
4
I want to say 3.
Negative 8 over 3.
minus 8/3
Plus 4.
plus 4. And then we need to subtract what we get when we plug in 0.
0.
0. What is going on? Why am I getting a positive number over here?
Same reason you're getting a negative number on your first sheet.
Are you getting a
I think
negative?
you calculated it to be a total of negative area.
you minus the area?
The integral from 0 to 2 of f of x should be giving us a negative number.
You're minusing this, so it gives you positive.
Well, yeah, so this should come out to a negative number.
And it is
What are we doing wrong?
not.
The integral of that is x to the 4 over 4 minus x cubed over 3 plus x squared.
I don't know, but I bet if you continue, you will get the opposite of what we're supposed to have.
Did you flip the sides on it?
Not only is your second number a negative, but so is your first.
What on earth did we do
Because you're
wrong?
on negative 19 volts.
Plug 2 into this. What do you get?
16. 4.
8 minus 4 plus 4 is 8. Plug 2 into this, what do you get? 0. We definitely did something wrong.
Oh, what?
So what in the insane are we missing?
Did we miss?
Factor out an x, we got x squared minus x
You
plus
would
2.
have had a negative 2x somewhere in there, wouldn't you have? If you look at the way
This?
you know?
We're looking for numbers that add together to be that. That should be a minus 1.
You sure?
Pretty sure.
Uh,
Negative 1 times negative 2 is positive 2. But now when they add together, it doesn't give me that.
You can't factor it out because
You can't factor. Did I write my problem wrong? That's a minus. Okay.
Oh.
Then now this will be a plus.
Oh, I see.
All right.
Good job.
Okay. That is so funny that still ended up when it was all said and done. Okay. Let's make sure everything makes sense here. Plug 2 into this, what do we get?
8.
8 minus 4 is 0. So at 2, we better get 0. Plug 0 in, we better get 0. Plug negative 1 in, what do we get? Negative 1 minus 1 is negative 2. Plus 2 is 0. Okay. Back to sanity land. Plug in minus 1/2 to this. We get negative, negative, positive, which is positive. Plug in 1 to it. We get positive, negative, positive, which is negative. We're chaining them. Okay, there's f. So now let's calculate big F of x. That's going to be x to the 4 over 4 minus x cubed over 3 minus x squared. Did I do that right? And so now our integral from negative 1 to 0 of f of x is going to equal f of 0 minus f of negative 1. And our integral from 0 to 2 of f of x is going to equal f of 2 minus f of 0, right? Everything I'm doing makes sense, right? F of 0 in both cases is just 0, so we don't need to worry about that. And so now let's calculate this one. This one is negative. What will we get when we plug in negative 1? When I plug in negative 1, I get 1/4 plus 1/3 minus 1. Did I do all that right?
Yes.
Okay. 1/4 plus 1/3 is 7/12. Minus 12/12 is negative 5/12. Make it negative is positive 5/12.
Yeah.
Okay. That's much better. That area should be less than 1. Okay. And for this one, let's see what we get. Here we're just going to plug 2 into it. 16 divided by 4 is 4 minus 8/3
Minus 4.
minus 4, which is going to be negative 8/3. And now our area is going to be this one minus this one. So our total area is 5/12 minus 8/3, or minus negative 8/3 is plus 8/3. What is 8/3 in terms of twelfths?
32. So you have 37 twelfths.
So we got 37 twelfths. Okay,
What do you have before?
37 twelfths. It doesn't matter, but I got to a point where I knew what I was seeing was impossible. 37 twelfths is correct. Okay, we did it. Yay. Sorry about that.
That is the area of that.
That's the area of this plus this.
So we're not counting that as negative area.
We did. That integral comes out negative 8/3. So the integral from here to here of this curve is minus 8/3. So we added it.
Okay, so
Or so we subtracted minus 8/3, which is the same thing as adding it. This integral we knew had to come out negative. This one we knew had to come out positive.
why did our area come out positive when it's obviously more negative area there?
Area can't be negative. That concept makes 0 sense.
Okay.
Our integral spits out a negative number when the area is under the curve. So if the area is under the curve, our integral spits out the negative of the area.
So we minus the negative area to account for that? Or the negative number to account for that?
Right, so the integral from 0 to 2 was negative 8/3. And the integral from negative 1 to 0 was positive 5/12. And so the area was the absolute value of those things. Area is the absolute value of your function integrated over it. That's what area is defined to be. Okay, I think we're good. Any other questions?
Wait, so that means when we take the area of, or the integral of the sine function, then we get 0.
That wasn't giving us the area, that was just the integral.
That's just the integral.
We could get the area, we'd have to do the absolute value.
So what is the area of the sine function?
From where to where? If we did the cosine function like we had over there from 0 to pi, then the answer would have been 2.
Okay.
Or, is that, yeah, that's a cosine function. Okay, any other questions? Anything we need recorded? I think that is it for, no, that's not it for chapter 5. We still have 2 more sections. So, you don't have to worry about your chapter test yet.
Are we getting
Not next week, but the week after that.
Are we getting the application of integrals after this?
Yeah, that will be chapter 6. So 5 is integrals. So next week we finish up chapter 5. The week after that we take our chapter 5 test.
Wait, so what's more in chapter 5?
What's what?
What's left in chapter 5?
We're going to do, I think we have U substitutions for calculating integrals, and
I would imagine.
I don't remember the other one.
That's chapter 6.
Chapter 6.
That's in chapter 6. So what's left in chapter 5? We have indefinite integrals and the substitution method, and then substitution and area between curves. So focus more on area between curves. Okay, anything else? All right, we have the rest of class for working on homework. That was a big one.